Yeah, so first things first, I'm a bit concerned about complexity,
Okay.
the notation.
Okay.
Um, I generally understand the concept, but when it comes to complex algorithms, not like a loop that has, let's say, O van,
Okay.
but essentially, especially with when we have to think about logarithms, or to, I'm not sure how to treat problems like these when we have to look at a piece of code and figure out the complexity
Right.
there.
Well, so in general, the answer is you got to look at how many. So so you have kind of some kind of function f,
Mhm.
and what you want to know is again kind of what's the runtime of f proportional to in terms of the input, right? So it might be that the answer is something like the runtime. So for example, the runtime it's like length of L squared plus 3 or something, right?
Mhm.
So and let's make it kind of more general, like something like this. So how would you find out something like this? Well, what you would say is, all right, how many operations does F perform, right? So for example, the easiest kind of situation is you're doing something like this. So how many operations is that? Well, basically, you're saying this takes whatever, let's say 5 operations, and then line 4 repeats length of L times, right? So for that reason, it's 5 times length of L operations. And for that reason, it's O of length of L. In general, what you want to do is you want to say either implicitly or explicitly that you're coming up with this kind of formula for the number of operations, and then you're simplifying the formula. It's basically by getting rid of the constants and taking the highest order term. So how would you do it in general? Well, there is not a general method to do it, right? It's a case-by-case situation where you're coming up with some kind of way of doing it. So you asked about logarithms, right?
Mm.
So what would be a situation where it's logarithmic? Well, the situation would be that so this is like this the simplest case is like you're just gonna do something like this, right? So what we're saying here again, kind of how do you determine the runtime? Well, you basically say in most cases, how many times does this repeat? How many times would this repeat? Well, you're saying I'm starting with n, and then it becomes n over 2, and then it becomes n over 4, and so on, up until the point where it becomes 0. And then what we know is that in order to go,
Sorry, but
yeah,
is it only bigger than one? Because
no, not really, because 1 divided by 2 is 0 in integer division. So this we just know that going from n to n over 2 to n over 4 and so on, that takes log n steps, right? And specifically log 2n. So the reasoning would be so does this take the same amount of time every time? Yes, approximately. How many steps would it take to actually get from n down to 0 if you're dividing by 2 every time, that's log to n. So you can get that from just the definition of the logarithm, or like it's a common pattern where either going from n over 2, n over 4, and so on, down to 1 or 0, or going 1, 2, 4, 8, 16, 32, up to n, that's log to n. Right? So that's kind of this kind of situation. In general, what you want to do is kind of look at the thing that repeats the most often and try to figure out how many times does this repeat. You want to make sure that the thing that repeats actually takes the same amount of time every
Um, what would be a case that it wouldn't take the same amount? I guess it would be if we multiplied something, right?
No, so like the most common thing would be something like this. So let's say that instead of doing like n equals length of L, we say something like while length of L is greater than 0, and then we take like the first half of L.
Hello, Professor. Can you hear me?
And then we'll add like the sum of the current L. Right. So here it's the same pattern, right? So it's L starts out being of length n, and then it's of length n over 2, and then it's of length n over 4, and so on. But in order to compute the sum of L, well, you need to add up all the elements of L. So that would take time that's proportional to the current length of L.
Mm-hmm.
So that means that every iteration here takes time. So that would take time that's proportional to the current length of L. So this would not be O of log n. In fact, the first time that you do it, you would need to sum up a list that's of length n over 2. So if the first time that you do it, it takes time that's proportional to n over 2, that's like already faster than log n. Right. So that means that what would this be? I don't think it's actually going to be like a closed thing. So it's going to be, it is going to be, yeah. So it's going to be n over 2 plus n over 4 plus n over 8, and so on, plus 1 times k. So the k here is the constant, right? So each time this iteration takes k for some constant k times the current length of L. So the total runtime, or the total number of operations, is going to be something like this. And then this is just, that's correct. So this, like, you can do it as a formula. So this is like 1 plus 2 plus 4 plus 8. In this case, up to n over 2. That's not correct. And this is, so this is 2 to the 0 plus 2 to the 1 plus 2 to the yes, for 2 to the log 2 n over 2. And this is just because 2 to the log 2 n over 2 is n over 2. And now you can just substitute in the formula. So that would be like this. So that's correct. And this is k times n minus 1. So this is O. So I think this might I think, look, the first time that you're looking, well, we've had an example like that, but the first time you're looking at it, it can kind of come out of the blue. But the fact of the matter is, just kind of as you're studying, just systematize. Okay, we had two formulas for sum. So we had the geometric series and we had the arithmetic series. And then we had basically not a whole lot of examples, I would say, in terms of the patterns that you could have with those kinds of sums. Right. So just look again, kind of what's the thing that repeats the most often? Okay, next step. What is the runtime proportional to? A lot of the time, it's going to be the same amount of time every time. You just need to count how many times it repeats. Sometimes it would be that you have a formula, you have kind of an expression for, okay, in this case, it's going to be proportional to the current length of L. And then you just add everything up. Not always you're going to be able to come up with a formula for the sum. Sometimes it's just a sum. It is what it is. There's no formula. A lot of the time there would be some kind of formula. And the only ways to get there would be kind of arithmetic series or geometric series.
Okay, so those are the only two that we have to.
Yeah.
Are those posted anywhere, the series, or is it just like?
I mean, in your lecture notes. Yeah.
And when we have to, I couldn't understand very well the concept of the trees or the recursive trees when you were doing in class. We had, let's say, a recursive function, and then you started doing the trees.
Yeah.
I didn't understand the concept of the trees. And well, not the concept, but how to create them and how to, after creating the tree, getting to the complexity.
Yeah. So again, this is a little bit case by case, but the basic idea is so the concept of the tree is you start with, you call, for example, fib of n. Right. And then in order to compute fib of n, well, you need to compute fib of n minus 1 and fib of n minus 2. So what I'm representing on the tree here is that you're calling fib of n minus 1 and you're also calling fib of n minus 2. And then in order to compute fib of n minus 1, well, you need fib of n minus 2 and you need fib of n minus 3. So that means that here I'm saying you're calling n minus 3 and you're calling n minus 4. And then over here, in order to compute n minus 2, you need n minus 3, and you need, this is actually n minus 2, n minus 3. So that would be like this, right? So in order to compute fib of n, you're calling fib of n minus 1, and you're calling fib of n minus 2. In order to compute fib of n minus 2, you need to call fib of n minus 3, and you need to call fib of n minus 4. Does that make sense so far?
Yes.
Yeah, okay. So then what you want to do is you want to, if every call takes the same amount of time, you want to count up how many calls in total there are. Because if you know how many calls in total there are, you know what the runtime is proportional to. Right? So you would say, okay, like this was actually like one of the more difficult cases. But in general, what you do is so kind of the most usual thing when it branches out is you say how many calls on this level, and then how many calls on this level, and then how many calls on this level. And again, you add up the number of calls on each level. So in this case, you can do an overestimate. So the overestimate would be on the first level, it's 1, and then on the second, it's 2, and then on the third, it's 4, and so on.
But you say it's an overestimate because essentially we do the same, we call the same thing twice.
No, I mean, it's true that we call, well, it's true that we call the same thing twice, but that's not the reason that it's that it's an overestimate. So every time, could you keep the door open because it's gonna go. Basically kind of every time, like if you call fib of n minus 1 twice, like it's going to be computed twice, so it's going to take twice the amount of time. But it might be that so here the situation is that on the left you go n to n minus 1 to n minus 2 and so on, and that takes n steps to get down to 1. But in the right branch, you go from n to n minus 2 to n minus 4 to n minus 6 and so on. So while on the left, you're going to have calls remaining, on the right-hand side, you're going to run out of numbers, if that makes sense.
It makes sense that we will run out of numbers, but it doesn't make sense that the function will keep working.
Well, I mean, the function doesn't care about symmetry, right? So the function, like, it's just that it's not that it's so like the way it works, right, is you call fib of n, and then in order to compute fib of n, you need to compute fib of n minus 1, and you need to compute fib of n minus 2, right? And if fib of n minus 2 takes like less time to compute, well, like it just takes less time to compute.
But it's approximately 2 to the n.
Well, 2 to the n would be an overestimate. So you can approximate the runtime with 2 to the n. It's in fact a lot less, right? Because so it's like we saw in class, it's like actually 1.6 to the n, which is like a lot less than 2 to the n. So like 2 to the n grows a lot faster.
Sorry, but how do we calculate how tough the tree is? Like how many?
Well, I mean, the tree goes down to 1. And you just say, well, like it takes n. So on the left-hand side, it takes n steps to go from n down to 1.
Okay.
On the right-hand side, it takes less. So the tree is actually going to be like not symmetric.
I was wondering if you could go over the question 6 from last exam, which is like about this.
Question 6.
The 2022 final exam.
So which one?
So I'm a bit confused with 2 and 3.
Which
2 and 3.
two? So there's this one? Yeah, okay.
Yes.
So here what's happening is so what is happening here? So there's like several tricks here. So here there's while j is smaller than so here we're saying while j is smaller than I, j never gets reset. So here it starts out with I being 1, and then I becomes 2, 3, 2, 4, and so on. And then j here goes up to I, but doesn't reset, right? So let's copy this. So this is like that. So okay, so one way to approach this is to just say, okay, like what happens when I is equal to 1. So J is gonna be like just 1, and then it's not gonna become 2 because 1 is not smaller than 1, so it just stops. And then it's gonna be I is 2, so J is gonna be 1, and then it's gonna be 2. And then I is gonna be 4, so J, so notice that J here doesn't reset, so J is gonna be like 2, 3, 4. And then I is gonna be 8, and J is gonna be this much. And then I is gonna be 16, and J is gonna be like this, right? So, and then eventually I is gonna become N. So here, what does it like? So here in total there is 2, 1, sorry, 1, and then this is 2, and then this is 3, and then this is 5, and then 9 is 9, right? Yeah, and then this is 9, and so on. So what's the formula here? It's a little bit annoying, but the formula is gonna be basically it's like up to I, but minus the thing that happened before, and I is like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and so on, right? So this is gonna be 2 to the 0, and this is gonna be so it's like 2 to the 1 minus 1. Still just 2 to the 1. This is gonna be, so here I is 4, so 2 to the 2 minus 1, and this is gonna be 2 to the 3. So at this point you can start seeing what's going on, right? So here we're doing like 2 to the 3, but we are sorry, so this was actually 4. Oh no, this is correct. So this is like this. So here we already did 3, and then this is like basically 8 minus 3, right? So 2 to the 3 minus 2 to the 2, and this is gonna be 2 to the 4 minus 2 to the 3, to the 1. So 2 to the 4 minus 2 to the 3, and then there is like a plus or minus 1 here, because like basically we're doing like 16 minus the previous ones, actually plus 1. Right, so the idea is like here it would be 16, except we already did all of those, and then we are repeating the 8. And this is plus 1 and plus. And then if you repeat this, this is up to 32. And this would be like 32 minus 8 plus 1, so like this. So the pattern here is basically there are the plus 1s here, but you're saying like this much plus 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 this much, and so on.
Why minus 8?
Because we had yeah, that's minus
16.
no, 9. Yeah, so sorry, there's no plus 1. So essentially, like the plus ones honestly don't really matter because like basically what happens is you're doing like this and then plus this and then plus this and then plus this. So the powers all cancel out except for the last one. So at the end, it's going to be I is equal to n, and that's going to be approximately 2 to the power of log to n. Which is n. Right. So the basic idea here, like the plus or minus ones, are just like basically not really relevant. The basic idea is the pattern is you are going up to, in this case, 2 to the 3, and then you've already done this. Right. So you need to subtract the previous power. This is definitely plus 1. And then here again, you go up 2 to the 4, except you've already done those guys. So you subtract 2 to the 3. Okay. And then you go up to n, which is 2 to the log to n. So that's like a common pattern. And this is just n. So again, like here it would be 2 to the log 2n minus the previous power. So all of those cancel out, and you get to just 2 to the log 2n over here. Is that making sense?
Sorry, about the last part, could you go back to the, what you're,
Yeah, like this is a
no, I mean to the right,
oh, and there's nothing there.
there's nothing there, okay, sorry.
Was this all like?
Yeah.
Okay. And that's assuming that the sum is constant, right?
That the plus is constant. Yeah.
What is what operation, like what built-in functions are constant, right?
So you will be so essentially kind of for integers, basically none of them, but usually you would be told to assume that the arithmetic operations are constant time.
Well, what about like list dot extend, all those list operations?
So list dot extend. So again, kind of you will be told if you need to, but basically just think about, okay, like what would I need to do in order to extend the list with k elements, where I would need to relocate k elements somewhere else. So it's going to be proportional to k. So if you're extending with a list of length k, that would be an operation with a runtime that's proportional to k.
The solutions for this exam,
Mhm.
it says that it's either O of log of n or O of infinity. But there is some,
Oh, so is that so yeah, so this is just because I think there was like an infinite loop there somewhere. So we said while j is smaller than I, that is definitely fine.
The one had infinite loop is that the ij sum is all 0, 0, 0.
yeah, that's what I wanted to mention.
Yeah, but it's not.
Oh, so I guess I fixed the yeah. So I guess it was that maybe it used to be like 0, 0, 0, and then we accepted like
The answer
it's
is
an
log
infinite.
of it?
Say again.
Pardon?
You said the answer, the other answer is log of it?
Yeah.
Yeah,
O infinity of log n.
Yeah.
Yeah.
Why?
Well, did I say log n?
Yeah.
That's,
it says if I was 1 and J was 0.
No, so like if I was 1 j0, yeah. And then if it says of log n, that is not right. Oh, because Oh, sorry. Yeah, okay, sorry. So it's that when it's when I said J smaller than I. No, sorry, that's just a mistake. It should, like, this is correct.
But if you switch it to J smaller than N,
Well, no, so like if I say J is equal to 0, sorry, if I said like I is equal to 0, so I think initially it was like something like this, then I times equals 2 doesn't change
that's an
anything.
infinite.
Yeah.
But what if it says J is less than N? That would be all of log N, right?
If I say J is less than N, so that would be a whole different thing again. So that would be like basic. So that would be kind of like a less annoying thing to to do actually. Or it would be still a little bit annoying because but here I would go up to N every time. If I go up to N every time, then so basically the first time it's gonna go up to N, and then the second time it's gonna go up to, I suppose, so like if we don't reset J,
Yeah.
right? So the first time it goes up to N, and then it's gonna be done because J never resets.
Yeah.
So it's gonna be just all of N.
All of them are log.
Yeah. All of N, because it would have to go up to N the first time.
Oh, so we ignore the I loop because it runs less.
Yes. Well, so like this would take time that's proportional to N the first time, and then it wouldn't take any time after that. So you still would need to say, okay, how many times does this repeat? And the answer would be log to N times. So this running the first time would be proportional to N, and then this would run log to N times, except the one time it would take time that's proportional to log to N. To N.
Okay. But for big O notation, we just drop all the other lower power terms.
Yes, so you just keep the term. Well, I mean, technically you can keep everything, but if you want the simplest possible form, you would drop everything that's not grows as fast as the fastest term. Oh, the screen is not shared.
I remember you talked about this in lecture, like there are some cases for time complexity. Like so some cases that we work through. Can you go over that again?
What do
Like there's some, cases like there's two loops, there's like is there like a systematic way I can analyze time complexity?
I would not say there is a systematic way. I would say like I would say there are kind of like the examples that we've done over several lectures. So it would be difficult to go over all of them.
Oh, okay.
I would say there are like the simple cases where, so like I think what you're referring to is like for I in range and for J in range, K, whatever. And then like this is just a constant thing. This would be O of N times K.
Yeah.
So this is kind of what you're referring to, like, so with the recursive functions we had, and maybe that's what you're referring to, is like we had like the 5 different tree shapes.
Okay.
Yeah, so let me see what people are saying in the chat. Yeah, so IJ, yeah, I guess that is, so why is that O of N squared and not O of N cubed? So this is because here I goes up in steps of n. So if you go up from 0 to n, 0 to n to 2n to 3n and so on up to n cubed, that's n squared steps.
Yeah, because I do doesn't reset, right?
Right.
Okay.
Well, the inner loop only happens the once because J does not get reset. Five different tree shapes. Okay, okay, sorry. So actually, like someone asked me to go on Discord. Where is the question? How is that of log n? Well, that is so like the way to think about this question is to think about how does IJ change, right? So here basically what happens is we're saying we start with I being length of L over 5, J being length of L over 2. And then we make one call every time. So either it becomes that it's I and I plus half the difference, or it's I plus half the difference in J.
Is this recursive binary search?
Basically, it's not exactly like it's not really binary search, but it's like a little bit analogous. So basically what happens is like I minus so J minus I initially is like whatever 0.0.5 n, right? So 1/4 minus 1/5. And then either IJ becomes I halfway from I to J, or it becomes I plus halfway from I to J up to J. So this is like a good example of kind of drawing a call tree. So you start with IJ.
Yeah, recursion is strong country. You draw a country, you don't draw the base case, right?
Yeah, well, we start from the bottom, right? So this would be like 0.2 and 0.25 n, right? So like length of L over 4, length of L over 5. And then one of two things happens, right? So either this happens or this happens. It's not both. And what is this? Well, this is again, like I is I and J becomes halfway between I and J. Or this I becomes halfway between I and J keeps the same, right? So let's say that it's the first case. So this would be like 0.2 n. And then kind of like halfway. So this would be like 0.225 n. Right. And then let's say it's the first case again. So this would be 125 n and so on. Right. And that's up until the point where J minus I is just the same. So you can say, okay, so we start with J minus I being, so this would be 0.5 n. And then it's half that. And then it's 1/4 that. And then it's eighth, and so on, up until j minus I is small or equal than 1. So here, instead of going from n to n over 2, n over 4, we start with like 1/20th n, but that's the same, right? It's like, how long does it take to get from here to 1 dividing by 2 every time? Well, it's log of this, which is log of 0.05 plus log n.
Log base 2, right?
It doesn't really matter, those are all proportional, which is of log n.
So do we not care about the other if statement?
Well, it's just that it's always the case that it's going to be this. Right. So like it's either going to be this or it's going to be this. And either way, I minus j minus I shrinks by a factor of 2.
Oh,
Right. Okay. So I think we had like a request for the call trees. So the basic idea is kind of like this. So the simplest one is like the factorial. And that's like you start with n, and then you make a call to n minus 1, and then you make a call to n minus 2. And so on down to 1. So that's n calls. So then the other linear case was something like this. So this you start with n, and then you go down to n over 2, and then you go down to n over 4, and so on down to 1. So that's of log n, again, assuming each call takes the same amount of time. So, so then you have the branching, right? So something like this. And I think it might be more useful to kind of look at the notes, because like I can only do it like fast, because this takes like an entire lecture if you don't do it fast. So that's like n minus 1 and minus 1, and
2 to the n. Right?
yes, and then this is like n minus 2 and minus 2, and so on. And then the accounting is like 1, and then this is 2, and then this is 4, and so on. So n steps. So this is 2 to the n. And then the sum of this is of 2 to the n, because it's 2 to the n of 2 to the n plus 1 minus 1. And then you can have like this. So you make 2 calls, but you go to n over 2 rather than minus 1. So that's the same kind of thing, except this is n over 2. And this is n over 4. And then you sum all of those up, and it turns out that that is O of n. So this is like 1 plus 2 plus 4 plus 8 and so on, plus 2 to the power of log to n. And then you have this. So the example we had was merge sort with the same kind of thing, except the runtime on each level turned out to be proportional to n. So that turned out to be n log n. Again, kind of like only so much I can do without having it be a 2-hour lecture. But those were kind of the shapes. All right, was there another thing in the chat? What if it is always case 2? Like, it doesn't matter if it's case 1. Sorry, I'm not sure what this question is about.
J minus I1.
Yeah, like it doesn't matter which way it goes, right? Because either way, J minus I just gets cut down by half every time. Right, so here,
Also, like, you should look at the exit condition of the recursion, right?
right. Sorry, so where was this actually? Oh, this was in Discord. Yeah, so it doesn't matter which way it goes. Like, what's important is that the gap here shrinks by a factor of 2 every time.
Was the runtime log of n for that?
Say again?
Was the runtime log of n?
For
the J minus I1? It was log of n.
okay. Yeah, it was, yeah. Yeah, because like you focus on like what is the gap between J and I, and it shrinks by 2 every time. And every call takes the same amount of time. So yeah.
I have a question about
Mhm.
recursion.
Okay.
So this is still one of the exercises that were posted.
Mhm.
Specifically the one that's about print 0 to n.
Okay.
So I just want to understand what's actually happening when this function is called. My friend tried to explain it to me, and essentially the way I did the here, let me. There we go.
So like something like this.
Right, so this one.
Yeah.
Yeah, so he was explaining that like essentially the function gets called, like you print 2 and then it'll
Right.
print 1 and then that goes down
Right.
to 0.
Right.
I understand that, but I don't understand the going backwards process where it's like the function is called and that's what actually causes it to print. So like where's this, is it stored or like what's happening there?
Yeah, so the way to think about it is kind of like this. So this is this situation, right?
Right.
So you first print, you first call and then you print.
Right.
So the way to think about it is like it's the same as using any other kind of helper function. So you wait until this is done and then you print, right? Like in the same way, like you call anything, like you wait until it's done and then you do this.
Okay.
And then in this case, what happens is the job of print n recursively is to print like 0 up to n minus 1, in this case, in reverse.
Right.
So, okay, like you wait until this is done, which is printing 0 until n minus 1 in reverse, and then you print n.
And then that's what causes it to go sort of like to loop back through and print everything.
Well, so it's so not exactly, right? So, in fact, this would not work. So let's kind of so this, wait, how did you write it exactly? That's not that. So that's like forward, yeah.
Yeah, it's
Uh,
0 to n.
So so 0 to n, so 0 to n would be like this. So basically what we're saying is let's do the opposite one as well. So this is reverse. Okay. So what's happening here is you're saying, okay, if you're printing 0 to n recursively, this should also print. So what we're saying here is, okay, in order to print 0 to n, first print 0 to n minus 1, and then print n.
Okay.
So what's happening when you call, let's say, print n recursively with 5.
Mhm.
So this gets executed. As a helper function, this gets called.
Mm.
The effect of that is to print 0 to 4, and then you print 5. Now, you can think about, okay, like what's happening actually when I'm calling print recursively 4? And the answer is, well, you first print 0 to 3.
Okay.
And then you print 4. And then when we're thinking about, well, what's happening when you call it with 5, it's that, well, you call this. If you agree that this prints 0 to 4, then all you need to think about is, well, like what it does is it prints 0 to 4, and then it's done. And then it prints 5. So what happens actually is, well, like that goes down to 0. And what's going to happen is this call is going to hang out until 0 to 2 is printed. And that means that the call to 2 is going to hang out until 0 to 1 is printed, and so on. So this guy is hanging out until the 0 to 4 is printed. Behind the scenes, all of that is going on, but this call doesn't need to care about that. Right? So here it's just the other way, in that you first print 5, and then you just call recursive, print recursive in reverse. So that prints whatever, 0 to 4 in reverse.
Okay, that makes more sense.
Yeah.
Yeah, it was easier to follow the that one,
Right.
The other one. Yeah.
Right.
That one seemed more intuitive to me.
Right. Well, like I mean, like I would say in a way, this one is kind of like straightforward in the sense that like you're done with n. Yeah.
Exactly.
Yeah.
Whereas this one, it's sort of like keeping it somewhere.
Yeah. Yeah.
Okay.
Yeah. Yeah. Well, so like, but like it's still keeping it, right?
Right.
It's just that here you don't need to say, oh, like, and after that I'll print that. So the tree is going to look exactly the same.
Right.
And print n recursively 5 is not going to return until print n recursively 4 returns.
Right.
And that's the same here.
Okay. Okay.
Yeah.
Thank you. That makes more sense now.
Yeah. Is the deepest layer of recursion done first? And since the function can only output one, deepest layer of recursion is done first. Yeah, so I mean, I would say, yeah, deepest layer of recursion is done first is true. So that's just because, like, if a layer is done, like I would reverse it. I would say whatever is done first, that must be the deepest layer, because if a layer is done, then it's not possible that it called something, but that's not done. But the caller is done because So like the way I would think about it is, again, kind of just think about this thing. Like it calls our helper function. It needs to wait until the helper function is done, and then it can go to the next line. It's true that kind of, so like if it calls a helper function, that's like one more layer deeper. And then the second quote is, since a function can only output when its helper is done. Yeah, okay, yeah, that I guess that's what you're saying, right? Then 3 to the end. Yeah.
On the topic of the recursion exercises,
Mhm.
could you go over the is prime algorithm? Because I wasn't able to come up with an algorithm even for this, like the base case and the recursion.
Yeah, well, so like the way to think about it is basically like, let's first write an iterative version.
Okay.
You can use like a default variable.
Yeah, that is the idea. Yeah. So you kind of do it like that, and then so just, you know. So that's kind of the basic idea. That's like the usual thing, right? That we do just with a for loop. So then we can convert it to a while loop. So that's the same. It's just that instead of a for loop, I just do a while loop. Right. And then we do, so kind of is prime is not the easiest example, right? But basically we had this idea of how you would convert from a for loop to a while loop, right? So I'll do like power while. So I'll just quickly do a power with a while loop. That's like this. No, I don't want it like this. So is this example okay? Like, is this fine? So yeah, so then you can convert it to a recursive version. So that's like that. So this is like the same thing. So we send result times x to result, and we send I plus 1 to I. Right?
I'm not sure I understand the logic.
So the transformation here is we're saying, okay, like in this while loop, so we start with result equals 1 and I equals 0, and then every time we multiply result by x and we add 1 to I. So here we're saying the same thing. We're saying if I became n, then we can return result. Otherwise here, so we send result times x to result, and we send I plus 1 to I. Does that make sense?
No.
So the call tree here is gonna look like this. So we start with result 1 and I being 0.
It's like using recursion to write a for loop, right?
A while loop, yeah, basically. So, and then we'll call it like this, and then result here is x and I is 1. And then we call it like this, and result is going to be x squared and I is 2. And so on. Up until the point where result is x to the n and I is n. And then this would just return result. And then the next one just returns result, because here we're just saying like return whatever this returns. right? So once we return, like everything just cascades down.
I see.
So
Can I do it?
yeah, so that's like also from lecture, yeah. So
Is there a difference with like returning this block and not returning this block?
returning, what do you mean? Like without returning it?
If you don't return this
Well,
block,
like you don't return, like there's no recursive call.
in some cases you don't return, like when you do the print.
Oh, well, yeah, I mean, like if the job of the function is to print, then it prints, right? But here we're actually doing a computation, so there's no, you cannot not return. Because like with print, like if you're processing a list or something and you're printing things, but like line by line, you can do it. But here we're actually like doing a computation.
Okay.
So in this particular case, if all you want to do is to print, you can say like instead of saying return res, you can just print this, and then at some point it will have printed, and maybe that's enough for you.
So in this example, how does the computer know that res starts at 1 and I start?
It wouldn't. You'd have to tell it.
And is there a way to like?
Yeah, there is. So you can specify that by default. So like the way we haven't actually done it in class. So the way you would do it is like you would just say like power xn, and then you would just call this as a helper function. Now you can also specify it as like what's called the default parameter. So you could say if I don't say what res is, if I don't say what I is, it's going to be 1 and 0.
So if the user just inputs an X and an N, then the program will still run.
Yeah, it would just, yeah.
So if we call parameter, that means that's the initial value. That's
Well, it's not like exactly like in practice, it acts as an initial value. Yeah.
so here we would write power while rec x comma n, and that's it.
Yeah, you can do it. Yeah.
When you are returning ally, what is it returning?
Returning this guy.
Oh, yeah, what is it returning?
Well, it returns whatever the next call returns. And what happens is you go up the tree. So you say, well, this one is going to return whatever this one returns, and this one is going to return whatever this one returns, and so on. And then that means that eventually, like this one is returning res. So the next one is returning res. So the next one is returning res, and so on. And res, when by res, I mean next to the game.
I have a question. I sent a code in the Discord group chat, and I have a question about the third question from last week.
Okay. Last question.
Yeah.
Yeah. Yeah.
Sorry, 3, not 7.
Oh. Question. Sorry.
Yeah, the dictionary.
Oh, okay. Yeah.
My code is in Discord. The code, like my answer for this question is in Discord, but like I think like logically it works, but it's not working.
Okay. The one.
It's on Discord.
Oh, it's on Discord. Sorry.
It's on ESC180 language.
Okay. Okay. Clean request. Set requests. For clean and clean request count. Okay. Keys, values, sorted values. Value defined, sorted values I. Index and original index. Index of value defined. List of keys. Index in original order. Keys. So here well, I mean, like, so like one issue that I see here is that, right. So one issue that I see here is that if you have counts that repeat, this would not work because index would just look up the original. That might not be the only issue.
I think you mentioned earlier in the question, there's gonna be no ties to the number.
Oh, there, yeah, okay, yeah. Yeah, okay, well, like, let's see what it returns.
Syntax.
Okay. And that's not what it's supposed to be. Oh, so it's like repeat stuff as well. So okay. Well, so I guess the question is, so I guess let me. Okay, so let's see. Yeah, so Maria, I'll ask you next. So list of keys. So okay. That's the list of keys. So then you have list of values like this. So okay. And then you sort the values. Well, you have a lot of ties.
Oh, so it's following the input.
Say it?
So I think the following is like the input. The input is not. The input doesn't satisfy the requirement. Like
Yeah, I mean that would be one issue. Yeah. So like so your in dot index thing would always look up the first one.
Yeah.
So
yeah. In the input there are no ties, then this code will work.
I mean, I don't know, but that might be possible. So sorted values is like that, like, yeah, so like sorted values seems fine. And then so initially you append socks, which I think does repeat 5 times. And I guess what was the output? Did it repeat a bunch? Oh, okay, it had different issues too. Oh, and then like eventually, so that was one issue, and then like you also just sort the answers. So that's just sorts it alphabetically, I guess. Oh, which you wanted to. Yeah. Yeah, that was a requirement. But yeah, like, so the ties is a problem. All right. Maria, do you want to ask a question? Yeah, that was required.
Yeah. Hi.
Sorry. So I think everyone here has to mute, or I won't hear the question. All right. Maria, do you want to ask a question?
Yeah. Do you hear me? Hello?
Go ahead. Yeah.
Do you hear me?
Yes.
Okay. Yeah, so I asked it on Discord as well, but is it possible to go over question 6 on the 2022 exam?
So everyone
It's just
in 2022. So okay.
Yeah.
Which question? Question 6.
Question 6B. Sorry, not A, B.
Yeah. Okay. So
Yeah, so why is
So-
it O log n and not O n log n? Might be a dumb question, but I'm
No,
just
no, no. I mean, in fact, it's neither. So where was it? No, like that's the same one that we did before. So basically the way it works is so there's several issues there. So one thing to note is that the J does not reset, right? And then I goes from 1 to 2 to 4 to 8 and so on, right? So when I is 1, this guy just does one iteration because 1 is not smaller than 1. And then when I is 2, it goes 1, 2, and then it stops. And then when I is 4, it goes 2, 3, 4, and then it stops. And then when I is 8, it goes like 4, 5, 6, 7, 8, and then it stops. Right? So
yeah.
So this is 1. This is 2 minus 1. This is so this is in fact, yeah, so this is 2. So like the pattern is basically this is 2 minus 2 minus 2 plus 1. And then this would be like 4, 5, 6, 7, 8. So this is like 2 to the 3 minus the stuff that we haven't, that we don't repeat. So the stuff over here, and then plus 1. So this is like 2 to the 3 minus 2 to the 2, and then plus 1, because we always repeat 1. And then this is
which one do we repeat?
The 4, because like we go up to 4 and then we do the 4 again.
Oh, okay.
And then this is like 2 to the 4 minus 2 to the 3 plus 1, and so on. And we go up to 2 to the log 2n minus 2 to the log 2n minus 1 plus 1. And that's because
Well, it cut out. Hello?
yeah, we're back. So yeah, and then this is so, and then we go up to 2 to the log 2n minus 2 to the log 2n minus 1 plus 1, because this goes like I is 1. So sorry. So yes, I is 1, 2, 4, 8, and so on up to n. So I up to n. So that's the same as I up to 2 to the power of log 2n. And then we add all of this up, so it kind of just cancels out, right? So like this plus this, like the 2 to the 2 is canceling out, and this plus this, the 2 to the 3 is canceling out. So what you're left with eventually is just 2 to the log 2n, which is just n.
Oh, okay, that makes sense, yeah. So in the future, for recognizing O log n, do we just draw the same thing? Not
I
draw,
mean,
but
I would
write
say
out.
this is like more of a one, like this was like a quite challenging question. Like I would not say that like there is a pattern to be made here, because like this is just like just figuring out how many iterations, and that's like not an easy question, I guess.
Okay. All right, well, thank you so much. I'll go back to
Sorry,
practicing.
like there's not just like not always there's a pattern, right?
Okay. Thank you.
Sure. Right. Okay, I got to go soon, but like one last question, if anyone wants one. Yeah.
Oh.
Two questions actually.
Okay.
I think we're going through this while I step in, so I kind of missed it. Like, why is it in, like, I get this layer of while loop is in square because I is updated by n, but like,
right,
why is the second layer?
So it's just that the j does not reset, so this just runs the ones.
How come j doesn't get reset? Like,
well, I never said. Well, but I never said like j is back to 0. So j becomes n the first time around. And then, well, because you say like while j is smaller than n, j plus equals 1. So j becomes n.
Yeah,
and then it becomes it stays n.
Got it. And this one.
How
is it not in square? You do this.
Yeah, so this is the shape.
Which one was that?
Wait, did we not do that? Yeah, we did. Yeah. So this is this. So this is like 1 plus 2 plus 4 and so on.
Oh, the geometric series, right?
Yes. So, well, I mean, so it's geometric series with the last exponent being log 2.
But we'll be given that formula on the exam.
Which formula? No.
Summation of. Oh.
At some point, you got to memorize it. Might as well be tomorrow.
So it keeps dividing itself by 2 each time until it reaches 1.
Yeah.
So it just doesn't matter that it's 2 of them.
It very much does. If it was one of them, it would be like this, which is all of log n.
Is there a pattern? Like if it's 3 of them plus together, what are they gonna?
It will be 3 log 3 something.
No, that's like
3 to the power something, right?
No, so that's like I think that was actually a 2022 question, which was like not easy. So
none of them are easy.
Say
None of them are easy.
no, I mean, like I would say like this is just like standard. Like it's like and to the power 3 halves. So if you just look at, I think it must have been last year.
I think it was about 3 to the power of log 2, man.
Yeah, that's right.
Yeah.
Which is the same. because like 3 to the
Yeah.
power of log,
Yeah.
that's like actually n to 3/3.
It-
So
It's
the-
always like a summation of a geometric series.
right, but like that was like a particularly gnarly one. So
Wait, this question 7. How do I do it?
this is like this one, yeah.
This year's question 7, like
This year's questions, what
2022, question 7.
2022 question?
Oh, it's the
Yeah, it's like,
Charles Babbage one.
Yeah, so
is that like, am I supposed to solve this?
no, we haven't done this year.
Okay. What is this method called? Like,
What is this method called?
what is this technique?
I would say kind of enumeration, so enumeration of combinations, I guess would be. But yeah, we haven't gotten to this year.
Okay.
Easy question. Bucket sort.
Okay.
It's O-N, right?
So
Only for
it's
integers, I think.
so buckets, it's like it depends on the details, right? So if the size of the bucket is constant, then it's O of n.
Okay. And if it changes,
Well, then it's like O of max of n and the size of the bucket, which could be large. So like yeah.
thank you.
Question about bucket sort.
Yeah.
Because I went through the notes that
Yeah.
were uploaded on
Yeah.
GitHub.
Yeah, that's not there. Yeah.
It says bucket sort and counting sort.
Those-
But we've talked about bucket sort
Yes.
and counting sort as two different algorithms.
Yeah. So bucket sort is a generalization of
I see.
counting sort.
Oh, I see, okay. And then about bubble sort. As a sorting algorithm, I cannot understand the swapped variable.
So the
It's
idea
useless.
so
So first things first, the swap variable goes in the outside of the for loop.
outside of here it says while not swap now. So this wait. So it gets reset to true every time. And then it gets wait, why do it like this? Oh, here I do like this. I don't like this version. So like something like this. Just return. So basically, if you go through the entire list and you never swap, there's no point in going over the list again. Because you already went through the list and you never swapped any pair of neighbors, which means that the list is sorted.
I see. So return, but it would return L, right?
No, well, so here you're modifying L anyways, so you would just say return, and then the job of bubble sort is to make L so that it's sorted.
Oh, I see. Okay, so if we wanted to implement that algorithm now into another function to sort, because I that's how I did question 3 from December 2015. It was the one with the movies.
Yeah.
So I tried sorting. I made a list and I tried sorting it with reference to the dictionary. So my question for that was for the swap variable, what would I do? Because I can't say return, right? So it was because I'm inserting bubble sort into another function. So if I said return,
Yeah, I mean, like in general, like you just shouldn't do it. Like if you're inserting bubble sort into another function, like the more helpful way to do it is to just make it a helper function.
oh yeah,
but
but here
in
that I couldn't
so
use helper functions. That's why I didn't.
yeah, so like you could do break.
Break.
Yeah.
Okay, that's what I
Yeah,
did.
yeah.
I
So,
wasn't
but like
sure about
here, I don't. Was it like? Did it need to be recursive or something?
it didn't need to be recursive, but it said
Wait, why? No.
part marks may be given for clearly
Yeah.
documented but
Well,
accompanied by
yeah,
clear.
but like that doesn't mean that you can't. Like that just means that like if you
Yeah, but
do help a function.
it's part marks, but if I
Well,
don't,
yeah, no,
it's
but like that's
clear.
if like no. It's like if you don't give the actual solution, but maybe you do
I
have
see, I
help.
see, okay, but still, in the bubble sort, I would use, the dictionary,
Right.
so the
Oh,
dictionary,
did I not sharing again?
anyway, I think I understand it.
Yeah.
So, thank you.
Yeah, sorry about that. Wasn't sharing again.
Dictionary appends are using dot update, right?
Yeah.
The update?
What? Well, I mean, like you could think about it that way. Yeah.
So,
Yeah. I'm sorry, guys. I have to go. Yeah, I'm sorry. Yeah. So I like there's office hours tomorrow as well. Sorry, I
Yeah.
really have to go now.
for,
Okay.
Thank you so much.
Yeah. Okay.
Thank you.
Yeah. Sorry about that.
Kevin, for the dictionary update, that you said,
Yeah.
if we say,
It's really just like dictionary to update, and you just update an element. It's